Hey guys, welcome back to another episode of Simuleos. Today's going to be an absolutely fantastic day, I'm pretty sure. Maybe. I have no idea. Anyway, we're going to work on the dynamic Huffman trees. Now, yesterday, at about 30 minutes till the end of stream, I started talking to you about the Vitter algorithm, and I feel I did a pretty poor job of describing what the Vitter algorithm was and how it worked. So today, we're going to spend a good bit of time going through that, explaining all the motivations, and I'm going to do my best to describe exactly how the algorithm works. Now, forgive me because I'm still going to be a little bit vague at parts. I know that. Your job is to let me know where I'm being vague and what questions you have left to ask. So let me go ahead and see the end projects, Simuleos, and Huffman. And let's just go ahead and draw our tree that we've been drawing before. So let's do Mirage, frames, animation.gif. Okay. We've come a long way with this animation so far, and in my opinion, it looks pretty dang good. We've got basically the drawing of our entire Huffman tree. We then go through and with blue highlight each individual letter, and then we go through and we write down the string for each of the letters according to how you traverse the tree, and that's that. You know, it shows what we need it to show. Now, we've got a bit of a problem. What we need to do is we need to find a way to visualize a dynamic Huffman tree. Now, a dynamic Huffman tree is a little bit different. Instead of drawing a static tree like we have here, well, in this case, we've got to generate each individual node as they come about. We need a giant not yet translated node, which will always forever be not translated. And then what we need to do is we need to find a way to show the swapping of different trees. Which may or may not be difficult. I have no idea. And that's kind of where we're at right now. There's a lot of stuff to do, but I'm just not sure the best way to do it. Anyway, so let's go ahead and start by talking about what dynamic Huffman encoding is and why it's cool. So let's do Zernal. And guys, for some reason, I know why. Last night I spent the entire night editing my new YouTube video, and I know I normally do it on today, the day before it's out, which I suppose is a little bit annoying, but then again, I didn't really even finish up all of the videos for the determinate stuff until last week, so I'm not so worried about it. Luckily, this upcoming video I can do a little bit early because it's Huffman encoding, and we're almost completely done with the first half of a Huffman encoding video right now. Rather, we're done with one video for Huffman encoding. Hey, Everett. So, we can go ahead and get started and work on that one. However, the dynamic Huffman encoding video will take a little bit longer. Luckily, because I upload videos every 2 weeks, I'm uploading a video this week, then there will be 2 weeks, and then that time I'll upload the Huffman encoding tree, and then 2 weeks from there I'll probably upload the dynamic Huffman encoding tree. So I basically have a month until I have to get everything out. And I like that. I like the fact that we have extra time to work on things here, so if things go wrong, I could potentially switch to another simulation. We could do something really quick like cross products or curls or something like that. So there's a lot of ways sorry about that to approach this situation. Now, one thing I want to point out is that the Vitter algorithm here is probably going to be one of the more complicated things I've done on my YouTube channel for a very long time. In fact, it might be the most complicated thing I actually have up on my YouTube channel. So, forgive me if this is a little bit vague right now. It's going to be hard for me to describe in full detail what it is that we're actually doing. So, let's go ahead and start with the basic Huffman tree. The basic Huffman tree is, well, in a way basic, but still not the easiest thing to understand. First of all, what are we doing? We want to encode a provided phrase into bits by using, oh sorry, that meant to be an arrow, using the least number, how about lowest number of bits. What you ate for lunch? I think I saw pancakes. What you ate for lunch? I had lunch yesterday. Let me think. Hey, Gustorn. I had just a sandwich. I always have a sandwich. I haven't eaten. I don't eat breakfast until about 3 hours from now. So I eat breakfast at around 8. I do 2 hours of streaming, then I do an hour of working out. Then I eat breakfast after that. So it's gonna be a while before breakfast for me. Okay. So bits, using the lowest number of bits. This is the idea. Okay. So how do we do this? Well, in some sense, it's easy. What we do is we create some sort of frequency list of all of the different letters that are coming in. Oh, sorry, Everett. I missed that completely. I'm really tired right now, but I'm always really tired. So what do? It's going to be A, B, C, D. Let's say they all come in with the same frequency of 25%, 25, 25, 25. Now, how do we put these guys into a... how do we do the encoding? Well, what we do is we put all the letters down. So we have A, B, C, D, 0.25, 0.25, 0.25, and 0.25. Then we add these guys together, which are the lowest two, to make 0.5. Add these guys together, which are the lowest two, to make 0.5. And add these guys together, which are again the lowest two, to make 1.0. Then we go through and we say 1, 0, 1, 0, 1, 0, and we read the tree backwards in order to find the encoding strings. So A is going to be 1, 1. B is going to be 1, 0. C is going to be 0, 1. And D, if I can fit it in down here, is going to be 0, 0. And that is our encoding phrase. And this makes sense, because in this case, A, B, C, and D are all equally likely to appear, right? So it's not that big of a deal. Now, let's say instead of A, B, C, and D, we have a different tree. Page, new page before. We have A, B, C, and A comes in with a frequency of 25%, B comes in with a frequency of 25%, and C comes in with a frequency of 50%. Okay, well in this case, C will be up top with a frequency of 0.5%. Then we have A coming next with a frequency of 0.25%, and B comes in after that with a frequency of 0.25%. These guys add together to make 0.5. These guys add together to make 1. So now we have a new string set. We have A as 0, 1, B as 0, 0, and C as 1. Now, as a quick note, I want to point out that these are what we call prefix free. This means that C is not a prefix for A or B. In other words, there is no way while reading these strings for me to accidentally confuse A, B, or C. So let's try something. C, C, A, B, 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 A, C, 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 C. Okay, so let's just take a look at what this encodes to. 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. This is our encoding string. Okay, so let's just read it. So this first one, we see a 1. So it's definitely a C. This one, we see a 1. It's definitely a C. We see a 0. We see a 1. Definitely an A. Here we see a 0. The first 0 is ambiguous. We don't know whether it's A or B, so we look to the next one. And we know that's now a B. Again, ambiguous first 0, but we know what the second 0 is. B. B. A. A. Now, the next one is a 1. So we know this is a C. We know this is a C. We know this is a C, and this is a C. So even though we use 1s in A, because A starts with a 0, C is not a prefix. It does not start out A. So as we're doing the decoding, we know what it's going to be because we're always going to be reading. Just call them prefix codes, or at least, which is a bit counterintuitive. Maybe. I'm pretty sure these are called prefix free. That's what I was told. Let me think. Yeah, actually that is counterintuitive, right? Because if you call it a prefix code, I'll have to look up the terminology, but I've always called this prefix free. I might be wrong though, so I'll look into it. Anyway, the idea is pretty simple, that C is not a prefix to A or B, right? B is not a prefix for A or C, and A is not a prefix for C or B. The idea is just simply that as we're doing decoding, we never run across an ambiguous string. Okay, fair enough. Thanks, Gustorn. So, new page before. Okay, so now what's next? Well, let's imagine we have a rather awkward string. In fact, let's put down the string that we had before. CC, what did I put down? CCA, BBB, AA, CCCC. So let's do that. Oh, that wasn't what I meant to do. Let's see, it's probably down here. Yeah, CC, A, B, 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 C, 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 C. I think there's two A's before that. A, 1, 2, 3, 4. Okay. Both are used, but both people I've talked to call them prefix codes. Okay, I'll think about it. Anyway, okay, so in this case, if we go through and we add up all the characters, we'll find that we find C 1, 2, 3, 4, 5, 6 times. We find A a total of 3 times, and we have B a total of 3 times. Meaning we have C with a frequency of 0.5%, B with a frequency of 0.5%, and A with a frequency of 25%. Sorry about that, 0.25%. This is the same code we had before, so we have the same string as we had before. Now, let's try doing something. Let's try lowering the number of C's so that, let me see, how about we drop it by 2 here, so that now C comes in with a frequency of 0.6%. Oh, I'm sorry. Let me think. 4%. And B and A come in with a frequency of 0.3%. Okay? Now, in this case, we have a situation where C is still the most frequent. However, we have more B's at some point in the middle here, as we're reading from left to right, than we had C's. Okay, now there are some situations where you might imagine, because we have kind of a weird code here, where our C's are disjointed and our B's are all centered around the center, maybe there's a time in which we can switch this code around, such that instead of C always being 1 character long and B and A always being 2 characters long, maybe we can make it so that at some point B is 1 character long and A is 1 character long and C is 2 characters long, or something along those lines. And this certainly would help shrink the number of bits that we use, right? Because that's what we want. We want to use the least number of bits. So how are we going to do this tree? Well, this can be done in a number of ways. We could read it through once and do what we call a 2-pass Huffman algorithm. This is exactly what you would expect. We go through, we find all the frequencies by reading through the string once, and then we do the Huffman tree. That's exactly what we did in our animation that we showed just a second ago. So I think it's this one. Let's show that animation one more time. We went through, we had the phrase, Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown, and Jill came tumbling after. And then we went through and we listed all of the different letters that would appear in said poem. And then after finding all the letters, we would go from there. Hey, Woody Bants. Okay, so that's one way to do it. Now, we're going to talk about another way to do it. And this way to do it is significantly more complicated. It's called the dynamic Huffman code. Now, this has a couple advantages. One, we don't have to read through the entire code in order to create our Huffman tree. Two, we can, in essence, shrink the code for different areas of the code. So the code is now dynamic, so that at certain places we can lower the number of bits when compared to the static Huffman code. And these two advantages are definitely worth looking into. Now, one thing to point out, a lot of people for dynamic coding look up the LZW, right? Encoding scheme. I think it's LZW. Here, let me Google it real quick. Over here, LZW. Okay. Yes, that's the one. Limpel Ziv Welch encoding scheme. So if you're interested in learning about that, feel free to look up this. Its competitor, in a way, is the dynamic Huffman. Now, these guys do different things. Dynamic Huffman. But it should be noted that at least with the Vitter algorithm, they provide similar results. Now, really quickly, I'm going to get a sip of water because I'm getting a little bit thirsty, and then we'll continue talking about dynamic Huffman after that. Terribly sorry, I'm super tired. Hey, Aaron Hance, what's up? Okay. So, what do we need to do for dynamic Huffman? Well, let's do a naive case. And guys, I'm going to take a little bit of time going through the theory today. Reason being that I do not want to accidentally give off incorrect information, and I want to make sure that I understand it, and I want to make sure that you guys understand it, because this is not the easiest algorithm to do. Like I said before, when this is up on YouTube, it will be the most complicated algorithm I have done on YouTube so far. It's not the most complicated algorithm we've done on this channel. It's not, I guess, too far from it, but usually we do physics algorithms on this channel, right? So I'd argue that FDTD or, you know, maybe the DMRG stuff we just did, those would be probably the most complicated things. But this one's pretty good. Just finished implementing some triangulation for dynamic 3D meshes. Oh, that's actually really cool. Could you send me a link to a paper or something related to that? Because I've been thinking I need to implement dynamic meshing for one of the problems I have with research. However, I don't know if triangles will work in this case. I have to think about it. Maybe they will. We'll see. But yeah, definitely send me a link to a paper or something with a similar method. That would be incredibly useful. Okay. So, what do we have to do now? Dynamic Huffman, LTW. Okay. So let's do a simple thing. Let's take our string C, C, A, B, 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 A, C, C. Okay? So let's take this and let's do the encoding. So, first thing first, let's imagine creating a tree at every single point. The first tree is pretty obvious. We have our root node here, 1. We have C here. Okay? That's fine. So, for our first tree, C is going to be 1. For a second tree, we have 2, C. Okay? That's fine. C is going to be 1. Now it gets kind of interesting. We have C and we have A. Okay, so we have to combine these two together. So now we're going to have 3. We have C over here. And we have A over here. Okay, that's not so bad. Both are still 1 character long. Now it gets a little bit more complicated. We have B, we have C, and we have A. B and A at this point are of the same weight. So we'll say we have 4. C should still be the closest to the tree. That makes a good bit of sense. However, A and B should be split off over here. This, of course, means that A and B are now 2 characters long, and C is 1 character long. Okay, we have 1 more B, but in essence, nothing should change, right? Because C is still the most common. So, well, C and B are equally as common, so it doesn't really matter. We don't need to change anything here. So let's do 5, and we'll say A, B, C. Okay, this is just a very stupid and simple way to do the Huffman tree, but you can kind of see where we're going here. We're drawing our tree based on how many of the A, B's, and C's have come up. Okay, so now we're at 6, and at 6, something interesting happens. B is now more common than C, so we put B up here, we put C down here, we put A down here. The next, all of a sudden A and C are equally as frequent, but nothing really changes. So we do C over here, A over here, B over here. Next we do 8. And here, A is now equally as frequent as C, or as B, but we don't necessarily need to change anything. But let's do it anyway. We're going to do B, A, and C. Now, as C's become more frequent, these will switch, and these will switch, giving us the tree kind of that we started with up there. When we get to about 10, it's going to be C, let's see, B, A. Something like this. So this is kind of a tree that we would expect here, right? And this is one way to do the tree. It kind of makes sense. We just go through and at every single time step, we create a new Huffman tree. Now, this is great, but it's not exactly efficient to create a Huffman tree, right? Because as we've shown before, it is numerically costly. So let's think about doing this in a little bit of a different way. New page before. We do C, C, A, B, 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 AACC. Okay, this is our code. So what do we need to do? Well, let's think about how to do this with another scheme. Okay, instead of just creating new Huffman tree every time, let's create a single node that's not translated yet. We'll call it the 0 node. Okay, and what we'll do is we'll consistently translate this node. So again, let's do this somewhat naively. Okay, we start with C. So we create one node over here, which is C, another node over here, which is the 0 node, and we add one to these guys. The next iteration makes just about as much sense. These guys turn to 2s. Okay, next iteration, we add a 3 up here. C is still 2. We have 1 in this node, a 1 and 0. Okay, now the next thing we do is we add in a B, so it's gonna be 3. We do C2. We do 2. Now interestingly here, the internal node here is the same weight as C, and we'll come back to that in a second. Now we do A1, 1, B1, 0. Okay, this is fine. It's not so much different than what we had before, but it's clearly less efficient, right? Because here we have a situation where C is, how do I put this? Where C is 1 character long, A is 2 characters long, and B is now 3 characters long. However, let's keep going, because maybe there's more to it than this. So we add B again, and we get something like this. So let's do 4, C2, 3. And now let's go ahead and switch these 3 and 2s. So we're going to do C2, 3. Then we're going to do B2, 1, A1, the 0 node. Go down to 5. And here, B is now all of a sudden the same as C. So let's go ahead and switch those two. So we're going to do B2. Then we have 3, C2, 1, A1, 0. Okay, keep going. What do we have here? B again. I'm not going to create a new tree for this one because all that happens is we add this to be 3. So this is now a 6. We add an A. Not really much changes here except we switch the A and C. So let's do C2, A2, 2. This will change. Let's change it to a 5 and change this to a 3. And this is kind of how far we've gotten once we get to the A. Now, at this point, things do change a good bit. So we are at number 9, I believe. And here, all of a sudden, C's come back up here. So C3. Then we have, I believe, 6 in here. B3. I guess I failed to switch A and B before, but that's okay. Then we do 3, A3, 0, and this will change to C4. So our final tree is a little different than the tree we had before. And the reason I did this is just to show you that this is one kind of similar method known as the FGW method, or it's similar to the FGW method, but this is a little bit different than this tree right here, right? So this tree, we have C as 1 bit, A as 1 bit, C as 1 bit, and A and B as 2 bits. This tree, we have C as 1 bit, B as 2 bits, A as 3 bits. So we have a completely different tree, generated in a completely different way. However, this one, though it has more bits in the end, is still probably just as good. And that's because we created the tree dynamically. So at some point, C was the most frequent character, and at some points B was, and at some points A was. Basically, we manipulated the tree such that we never overused bits. The other thing that I'd like to argue is that this new tree was created dynamically, which makes it way easier, rather way less resource heavy. And that is incredibly important. Okay, so now let's do new page before. I'd like to point one thing out. Today, guys, we're going to be spending most of our time working with theory, right? So this next example is going to take a good bit of time. It's going to take a lot of thought, and I'm just going to point out right now that it's not easy to understand. I've spent a very long time trying to understand this, and I think now I finally get it. But I still screw up, so if I screw up, I apologize. Again, I need another quick sip of water. Apparently, I need one every 10 minutes. But we'll get started with the vidder algorithm, which is the algorithm that we will be implementing in just a second. Again, guys, if you have any questions up to this point, let me know, and I will totally answer them as soon as I see them in chat. And of course, if you've got any comments or anything that you need me to fix on stream, let me know about that too, and I will totally do that as soon as I see those comments too. Okay, let me check to see how many people are on right now. Okay, it's okay. So here's the thing. I would like to ask a couple opinion questions of you guys too, before we get started. The first of which is, should I advertise Twitch on my YouTube channel? On the one hand, I'm thinking it's probably a really good idea. On the other hand, I want to do it a little bit later. I think I'm going to wait till I have 1,000 YouTube subs before letting them know that I have a Twitch channel. And so I think I'm going to create like a channel trailer or something like that when I hit 1,000. Maybe 1,024 subs, just to kind of keep with a bit theme or something like that. But I want to let you guys, I wanted to kind of hear your opinion on that. The other thing too is I've been approached by a few people about adding donations to the channel. I've kind of said no to that up to this point for a number of reasons, but if you guys want, I can add that in. Again, it's going to be a while even if you guys say yes to that, because I don't know if I really feel comfortable doing donations. But anyway, the thing is, I just wanted to vocalize this. This stream is a little bit different than most other streams on Twitch. It's, first of all, incredibly linked to the YouTube channel that comes with it. And second of all, it does numerical things. I mean, we do computational physics. We do difficult computer science algorithms, at least difficult for me. And we don't do large projects either. So it's not like people can come in and they can check the progress of the game in like a week or something like that. We'll be working on a new project, right? So we kind of just zip through a whole bunch of different things. And that's, I don't know, it's just a little bit of a different idea. So if you guys think it's a good idea to accept donations or something like that on this channel, let me know. If not, let me know. I don't know. I haven't quite fully thought it out yet. It's just something that's been on my mind lately, and I thought I'd ask you guys your opinions. And of course, if you don't have any opinions, that's perfectly fine too. Okay, so now, onto the difficult stuff. I kind of wish there were more people watching for this, because this is going to be incredibly important later on, but that's okay. So, what do we need to do? Let's talk about the vidder algorithm. Now, the vidder algorithm is probably best described on the paper that was described by vidder. So let's go here. Let me check. It should be the very last one I added in. Maybe this one. Yes, it is this one. So I'll go ahead and link this over here. And this is probably the best description I have of the vidder algorithm, and it was written by vidder himself, which is good. It's good when people can express themselves, but the thing is, this wasn't actually very easy to read. The best information I got was from this little snippet here on page 839, and what I'm going to do is I'm going to pull out my copy of this really quickly. I just realized I don't have it out, and then we'll work on it. Okay, good. So I've got my copy out right here. And again, I'm on page 839. I use this, and I don't think there are any free PDFs. They don't have to be free. I have access to OpenLink, pretty much all the journal repositories you need. So let me think. Chapter 1, Introduction. Oh, it's not free as in it's a book. Oh, I was hoping for like a review article or something. That's okay. I'll take a look. If you want to give you money, why not let them? I don't know. My thing is, it's just... So I'm in a fine financial situation. That's why I don't want to do donations. Because at this point in time, I don't need money, and I don't care about money, you know? In the future, if this were actually my job, yeah, I'd do it, you know, I guess. But it's not my job. My job is being a PhD student at the Okinawa Institute of Science and Technology. So, I don't know. it's just weird to me, because what if there's some kid out there who has like no money whatsoever? He's living on his own. His parents, are not paying for him. Yeah, Aaron Hans, I have the same thing. Again, I'm a PhD student right now, so I can use pretty much all sites that you need. I was hoping for like a review article, but that's fine. Doesn't matter. Thanks a lot. I really appreciate it. But the donation thing, here's the thing. Yeah, what if there's some guy who actually needs the money and he's donating to me because he likes my stuff, and I'm like, I don't really need the money. Then I just feel like bad, really bad. I've been thinking maybe what I should do is wait a lot longer until I do the donation stuff, and then just kind of give people access to a shop instead, where they can give a tip at the shop, which is a little bit of a different mentality, but basically the same thing, that I've been thinking about that too. Anyway, lots of stuff to think about. Let's go one step at a time. Vidder algorithm. Okay. So, with the Vidder algorithm, we have a few things we have to take into account. The first of which is implicit numbering. Okay, this means that with every tree, we have a numbering scheme that comes with it. So, for example, let's say we have this tree here. I'm just drawing the nodes. I'm not drawing the letters inside of the nodes. Something like this. Okay, this would be 7, or let's say 5 up top, 4, 3, 2, 1. Okay, so going this way, we increase in size of the numbering, and going this way, we also increase in the size of the numbering. Okay, this is incredibly important to foretelling which numbers are where. Now, oh shoot, I missed a node. This is 6. This is 5. Yeah, good. Something like this. Okay, that's fine. Now. Oh, shoot, I missed 2 nodes. Dagnabbit. 6. 7. There we go. Now we're good. Okay. So, again, going this way, we read up, and going this way, we read up. And that's kind of the important thing here. Now, the next thing we need to talk about are blocks. And here's what I'm going to do. I'm going to change these guys from circles into squares. And maybe you'll see why in a second. Okay, so a block. And this is something I did a poor job describing yesterday. A block here is going to be all other leaves of weight 1. So let's give all of these guys weight 1. 1, 1, 1, 1. These guys weight 2, and this weight 4. Okay? So that means this guy, all of these guys are 1 block. These guys are 1 block. And this guy's kind of lonely in his own block up here. So these blocks are incredibly important for later. Now, we have another thing that we need to keep in mind, which is that each block has a leader. The leader is the top dog, the highest number in each block. So here's the leader there, there's a letter there, and here, of course, is a leader here. Okay, so then we have leaders. And finally, he has one more thing, which he calls the, what is it called? Invariant, I think. And this is relatively complicated the first time you read it. In fact, here, let me read what Wikipedia says about it. So let's go here. I don't need to check that. Here, what is it? Dynamic Huffman Vidder algorithm. There we are. Okay, so if we go down on Wikipedia here, the invariant is for each weight W, all leaves precede all internal nodes. Now, here's the thing. I had trouble with this phrase, precede. I didn't know what they meant by precede. All it means is that if we have leaves, which here are going to be squares, of weight, let's say 2, and we have, if we have internal nodes, so internal nodes here, and we have leaves here. Okay, the leaves come before the internal nodes. So we'll say 2, 2. They're all the same weight, but this is going to be 1, 2, 3, 4. The internal nodes are always higher than the leaves in the same block, rather of the same value. And one thing I have to point out is we do definitely keep the leaves and nodes differently for blocks. So for every number, we have two of the same. So let's go down here. We have weight 1, we have weight 2, and we have weight 4. Okay, so we have internal nodes. Let's say internal nodes, leaves, internal nodes, leaves, internal nodes, leaves. Okay, so the idea is that every time we have two different sets of blocks for every different weight, and we have the internal node weights and we have the leaf weights. Okay, so this is super important for what we're going to do next. So now let's write down the Vitter algorithm in a way that makes sense. Again, this is following from 839 of the paper that was just linked in chat. I don't know where the paper came from. I guess it's ResearchGate. So hopefully we're allowed to use it. Okay, so we do the same thing we did before. We have a 0 node, or sometimes called not yet translated, depending on how you're doing it. Okay, so we're going to read in a letter, obviously, because we're going to try to create a string dynamically. So we read in the letter first, okay? We go through and we ask a question. Is this letter the 0 node? If so, then we add let's see, elements to 0 node. And this will be a 0 and the letter. Okay, now we're going to keep the 0 node 0 for a while, and what we're going to do is this thing called slide and increment. Let me think. Leaf to increment. Well, Q, yes, slide and increment. Okay, and we're going to talk about this function in just a second, but it's kind of what you think it's going to do. We're going to move the branch around in the tree a little bit, and then we're going to move everything else around so that this makes sense. So slide and increment, but we're going to do the parent, not the node itself. Vientet. Let me think. Rest in peace, kick torrents. What do you mean? I don't... Did something happen to, like, torrenting or something? Okay. So, if else, so if, let's say, else, let's say if, I don't know, I'm doing bad notation here. This is what we're going to do. If we are not the 0 node, as in we already have the node before, the first thing we're going to do is switch letter with block leader. Okay, so then what we do is after switching this guy, we then, sorry about that yawn, guys. And again, this is going to be the highest leaf of the same weight. We then do the slide and increment. Again. Now, what is a slide and increment? The slide and increment is actually kind of complicated to describe. So first of all, in both situations, when we have our internal nodes being generated or something like that, we have... okay, so if the leaf is the not yet translated node, it's going to be the highest 0 node. The leaf is. If it is another node, like let's say L, and we already had an L, well, we've switched that node with the leader of its block. So no matter what, at this point, we have a leaf that is at the front of the block. And that's the leaf that we're going to manipulate. This is a super important detail. No matter what, the leaf that we've read in is going to be the top of its block. And this is important. Now, let's talk about the slide and increment. I'm going to say that squares are leaves. I don't remember what notation I did before, but I think I switched this up. And circles are internal nodes. Now, what we're going to do, it looks like you don't torrent. It was MM. It was the most popular public torrent index pro diver. Founder is arrested in Poland. The website is dead now. What about Pirate Bay? I thought Pirate Bay was like the most common one. Anyway, I do torrent a little bit, but it's mainly Linux distributions. So last time I did a torrent, it was for Arch Linux, I think. I don't really use too many things, honestly. Like I don't watch movies. I don't really play games. I don't really use software that's proprietary. So there isn't really anything I could think of to torrent, you know? I don't listen to music really either. That's not, you know, freely available on YouTube or something like that. So I don't know. It's not, for me, because I don't do so much with popular culture and things like that, torrenting was never really something that I found useful in a way. But that's just me. Other people I can totally understand. In fact, my roommate in college used to do it all the time. So I can totally understand why this would be a big deal. So anyway, let's keep going. So we have leaf nodes and internal nodes. Now what we're going to do is we're going to take our tree and we're going to shrink it, okay? And by shrink it, I mean we're going to do this. So let's say we have a leaf node of size 4. Now let's have a couple internal nodes. Actually, just one internal node of 4. Okay? Here. 4, 4, and then 5, okay? This is a representation of our block. Now again, I have refrained from putting numbers on each of these guys, but in essence, these guys are implicitly numbered, such that this guy has the lowest number, and this guy has the highest number. Okay, so we have the lowest number over there on the left, the highest number over here on the right. Now, obviously 5, this is the start of a new block over here that we're not going to pay attention to at this point. Now, let's say we have 4 at the front of its leaf block, and what we want to do is we want to slide and increment this guy. Well, okay, what we're going to do is move him in front of all of these internal nodes here, and afterwards we're going to add 1. Okay? So then what happens to all these other nodes? Well, they get pushed back into the previous position in the block. So for example, if this was, I don't know, 10 and this was 5, this guy moves to 5. It skips a couple positions, but it moves to that position. This gets a little bit complicated because these are all internal nodes, but we'll see how it works in just a second. So what happens? We do 4. 4. These guys are linked somewhere in here. We have some dots. Then we do 4, 4. Here's the leaf node again. These guys are combined. This guy turns to a 5. And then we have another 5 leaf node here going this way. Okay? Now, you might ask, okay, well this is great, but how do we update everything? Well, at this point, what we do is we start updating the tree this way. So we start with this node, and we kind of move up the tree, whichever way the tree needs to go. This way or this way. Okay? Now, let's imagine instead of having a leaf, we have an internal node, which happens quite frequently, right? In fact, right here, the very next node that we would update is an internal node. So let's do that one. So internal node. Here's what we're going to do. We're going to say we have a, I don't know, I'm just going to write down the numbers they have here on the paper. So it's 8. Then we have leaf nodes of 9. ... 9, 9. These are all of our leaf nodes. And then we have an internal node of 9. Now remember, the blocks are always going to be either leaves or internal nodes. So this guy right here is part of a block over here. These are part of this block, and this is part of this block over here. Okay, so these are all 3 different blocks that we visualized here. So what we're going to do is we're going to move 8 in front of all of these external nodes, in front of all the leaves. Then after that, we're going to increase its value, similar to what we did before. And we're going to shift all of these guys back. So it ends up being that this looks like 9, 9. These guys are connected somewhere up here, ... 9. Then we should have 9 here. Something like this. And then we go forward here. Now in this case, the one that we update is not this node here, because this node's still 9, 9, right? I mean, in the end, we had 2 9s that were being connected, and we still have 2 9s that are being connected. Instead, we update this parent back here, and we move forward from there.
So what we do is we start, usually, by incrementing a leaf node, and then we start incrementing other nodes. Now, how does this work in practice? Page, new page before. By the way, guys, I have to stress, again, this is an incredibly complicated algorithm. So if you have questions, comments, concerns, let me know, because we're going to get into an example now. And honestly, I think we're going to finish up with the example around 6 in the morning and then start doing programming. I have not decided how I'm going to do future videos of this particular season, saga, series, whatever it is, of dynamic Huffman encoding, because we're running into a situation where I normally like to go through the entire algorithm in the morning, just before starting streaming, or like just before starting doing the programming. However, here we have a bit of a problem. This actually takes a very long time to do, so I haven't quite figured out the best way to do it. What we're going to be doing today is more kind of theory. We're going to try to figure out how we're going to approach this algorithm, what we need to do in order to actually implement this with the Huffman trees we currently have. Okay, so now an example. The example is going to be simple. A, B, C. Okay, so let's start. We have our 0 node. First thing we do is we add an A0 and a new 0 node in here. Okay, this is for this A. Well, in this case, we're then going to take this block and we're going to slide and increment this block. Okay, well, it's already at the leader of its block. There's nothing here. So the next tree's rather trivial. It's 1, A1, 0. Okay, now we have a new letter, B. Okay, so this means we're going to add B in here, B0, 0. Looks good to me. This guy now has to be slid in front of all of the external nodes of weight, whatever it is, plus 1. So this means in front of all of the internal nodes, or all of the external nodes, all of the leaves of size 1, weight 1. So it's going to be moving in front of the A over here. And A then gets shifts downward there. So now we have 1. Here's our 0 node, B0, 0 node again, A1. And then we just increase the weights here, here, and go back here. Okay, so far so good. Now we have to add in this final one, which is a C. Gonna go down here, C0, 0. Okay, now this 0 is going to need to move in front of all of the external nodes, all of the leaves of length, wait 1 second, of length 1, of width weight 1. So that's going to be this leaf here. It's going to be moved up here. And then this guy is going to shift backwards to this position here. And this guy is going to fill the void over here. So it's going to be 2, 0, C0, 0, 2, A1, B1. Okay? And if you look at figure 7 on page 840 of this link right here, that is exactly what they have, which is fantastic. That means that we're good. So now let's say instead of ABC, we have ABCD. So let's go and do page, new page before, and let's do ABCD. And let's say this is the original tree, 3, 1, A1. Oh, I'm sorry, this is a B. B1, A1. 1 second. This is actually 2, 1, C1, 0. Okay, so now if the next one's a D, here's what we're going to do. We're going to add a D0 and a 0 node in there. This guy wants to switch with the highest guy in its next block, which is going to be here. And these guys all shift over respectively. So now we have a situation where the new tree is going to be 3, 2, these guys are a little bit different, 2, these guys are a little bit different. So we're going to say 0 node here, D0, 0, A1, B1, C1, where here, this node here increases. So this is going to be a 1 and a 1. Okay, so this is what happens if we have A, B, C, D. But now let's do a little bit of a more complicated case. Instead of A, B, C, D, let's do A, B, C, C. A, B, C, C. So same tree we started with, 3, 2, B1, A1, 1, C1, 0. Except in this case, we're going to increment C. So this is the one we're incrementing. Okay, so this is where things get a little bit complicated. C needs to move to the front of its of the 1 block right here. So first we switch it with A. Okay, do that. Then we increment it. So we go over here and we say 3, 1, A1, 0, 2, B1, C1. This now becomes a 3, and this becomes a C2. Oh, rather, I'm sorry, it doesn't become a 3 just yet. Sorry, this is a 2, this is a 1. Now we switch 1 with the front of its block, which is going to be over here. And then this guy over here is going to shift over here. Okay? So in the end, we're going to have, 1 second. Yes, we're going to have the following tree. So again, we do the C shift first. It's going to be 3, C1, 1 second, 2, B1, 1, A1, 0, right? And this is going to increase to 2, meaning this increases to 4. And that should be what we have. 4, 2, 1, A1. Good. So this is exactly what we have. And this is shown on figure 8 on page 841 of the link that I posted in chat. So this is how we would do the dynamic Huffman trees. Now, we could do more complicated trees, I will admit, but the more complicated trees we do, the longer it'll take to do, because this isn't exactly the easiest algorithm to just do analytically. Now, at this point, if you have any questions, let me know. I'm going to do a quick overview of how this algorithm works one more time. And if you need to see these examples again, let me know, because I will totally take a step back, do the examples one more time to make sure that you guys understand what it is that we're doing. For some reason, I need another drink of water. I'm getting super thirsty today, so I'm sorry, but that's how it goes sometimes. Okay. Sorry about that, I hit the microphone. So let's go ahead and talk about what it is that we're doing. A couple different notes here. So first of all, we have definitely split up the difference between internal and external nodes. Internal nodes are these ones in here. External nodes are these ones out here. Sometimes they're called internal nodes and leaves, and I've been kind of interchanging the difference here. Interchanging them here. Now, another thing to note is this tree is a little bit longer than you might expect the tree to be. If we did basic Huffman encoding, the A would be here where this 1 is. However, again, as I mentioned before, we put the least frequent and the last used, or the least used, or we put the least frequent characters at the bottom of the tree. We also put the characters that are used the farthest away, like they were used the farthest in the past, at the bottom of the tree. And it's assumed that these letters won't come up for a little while longer, right? And so the idea then is that even though this tree is a little bit longer, we're not using all the characters on the tree as frequently. You know, before we'd be using, you know, let's draw our regular old Huffman tree. Let's draw this guy. So we have all our dots being created. Let's just scroll down. So this guy, we have all of these different numbers that are being created. We use spaces most frequently. Then we use G's very infrequently, right? So we're probably going to be using this guy a lot and this guy very little. But at the same time, we don't know what's coming up when. Even here, we don't know, with the dynamic Huffman encoding, we don't know what's coming up when. However, it comes with the distinct advantage that even though we don't know what's coming up when, the dynamic Huffman encoding algorithm does its best to change itself depending on what we have been seeing. So this means that if we see a whole bunch of C's in a row, or a whole bunch of D's in a row, or a whole bunch of Q's in a row, the dynamic Huffman algorithm will be able to, more accurately handle that particular situation. And this is good for a number of things. In fact, the dynamic Huffman encoding algorithm can get pretty dang close to the theoretical maximum a lot. And a lot of times you need to use dynamic Huffman encoding because you cannot do the two-pass Huffman algorithm. So that's another thing to point out there. Two-pass Huffman is still incredibly quick, or incredibly small. So if you can do two-pass Huffman, it might be best to do that in most cases. But it's always good to check against the dynamic Huffman. And in fact, we will be doing that. We'll be using the same phrase, except using dynamic Huffman for it. And we'll see which one uses the least number of bits. Hopefully. This is actually something that I've always been interested in, because when I took my data compression course in college, it was definitely something that came up a few times, and I never really fully got the difference. You know, we did dynamic Huffman encoding in the class itself, but I never really fully understood the difference. Of course, the way we did dynamic Huffman encoding was a little bit different, so that's that. Okay, guys, that should be it for the theory block today. I haven't decided how we're going to do theory blocks in the future. But we've spent a good bit of time talking about this algorithm. I didn't see any questions, which means one of two things. It could be that you guys are completely and totally lost, or it could be that everything's super simple and you guys totally get it. In the first case, I apologize. Again, I kept asking for questions, so if you have any more questions, let me know and I'll totally answer those as soon as I see them in chat. Or if you're just generally confused, let me know about that. Otherwise, if you guys totally get it, then you guys are way smarter than I am, and that's totally understandable. I'm not particularly great at this computer science stuff. Okay, so what do we need to do from here? So let's look at this visualization. In the end, we want a visualization of drawing a dynamic Huffman tree, which is incredibly cool when you think about it, right? We should have the ability to draw an initial tree, rather start with a tree that's not doing anything, draw that tree, and then grow the tree from there. So that we grow different limbs and stuff like that. We can continually increase the zero node, and then we kind of shift things around so we can see things physically moving and moving, like, I guess, rotating through the tree and stuff like that. I've been thinking about ways to do this too, and I don't really fully understand how we want to go from there. Basakma, hey, thanks for coming in. Unfortunately, you missed an hour-long theory block, so I don't know how much of that I can repeat, but basically we're working on dynamic Huffman encoding today. If you have questions on that, let me know. Okay, so now we have to think about how we're going to visualize this tree. Yeah, Basama, definitely let me know if you have something that you want me to repeat, because it's going to get kind of complicated. In fact, it is really complicated. I'm not even going to... I've said that a couple times. It's not easy. Okay. So we got to think about how to do this visualization, but the visualization is going to come second this time. Whereas previously, I worried about the visualization pretty much from the start. Here, I'm going to have to do that at the end. So let's think about what we need to do. We have Huffman.h, and in Huffman.h, we have a couple of different functions. Now, what functions do we have? Let's go into that. That's fine if you want to do that. Not a big deal. So let's go into Huffman. I'm not in the appropriate directory. CD projects, Simuleos, Huffman. Okay, and you'll notice here we have a file called vitter. Where is it? Vitter.cpp. I've been planning this for a while, so let's go ahead and go into vitter.cpp. vi vitter.cpp. Good. So this has absolutely nothing in it, and we can go ahead and delete all of this kind of stuff. This was a while ago. Okay. Oh, sorry for the yawn, guys. Okay. So what we want to do is include, I think, Huffman.h. One second. Let's go into vi Huffman visualization.cpp. Oop, my bad. .cpp. Okay, what else do we need to import? I think, let's see, we might want like vitter visualization or something like that. I haven't quite decided how I want to do this. Let's go ahead and quit here, and let's go into Huffman.h. And let's see what we have. So we have struct position, struct color, struct node. We have node compare, which is great. Struct Huffman code point, Huffman tree. Then what do we have? We have node Q, create nodes, Huffman, create bits, encode, depth first search, two-pass Huffman. Okay. I think we need to fundamentally think about how we're going to do this, because there's a couple data structures in here that we need to figure out how we're going to work with. The first of which are blocks. Now, it's easy enough to add an implicit number to each of these guys, right? We can just do a depth first search. If we know how many characters there are, we should be able to figure out how many internal nodes there are. And then we just go through and we say, hey, if we're a leaf node, we're at this position. You know, we can, rather, if we have the maximum number of nodes, then all we have to do is go through and say, okay, we just, you know, we change the number around. It's not that big of a deal. Okay, the problem I'm having is how are we going to do, after the implicit numbering, how are we going to go through and, let me think, figure out which nodes are in which block, okay? So we have to differentiate between internal and external nodes, right? Where the internal nodes are obviously the ones here, these guys that combine at vertices. And the external nodes are obviously the leaves down here. Okay, so if we have a block, let's say all of these guys are all in the same block, let's say. I don't know if they are or not, but let's say that they are. Maybe they are. I can't really tell. All the ones of the same color will be in the same block. All the same color and size. So I know at least these 4 are in the same block. But that's okay. Okay. So let's assume that we have all these different nodes that are in the same block. What we need to do is somehow keep a simple way to get the positions of each individual block, or each individual block element, and switch it, rather move it around with the other blocks, elements in the block. So for example, we're going to have to implement the slide and increment function, which means that we have to move an element to the front of the block. And if we move the element to the front of the block, we then have to move the other elements back. That's going to be a bit of a pain. So, dang, I have no idea how to do this. Simple and tree nodes. What do you mean simple and tree nodes, Everett? I'm sorry, I don't fully understand. Okay. Now, the one thing is Vitter does have example code, but the example code is written in Pascal, and it's not exactly the easiest thing to read. So let's go through and let's see what we need to do. First, let's go into the Vitter algorithm, vitter.cpp, and let's see if we could just create a few different functions that we might need. So in main, here, let's go ahead and remove this. Right now we don't need anything, so let me just do this. std cout. What do I want? I want to say coming soon. Okay, end line. Good. So what functions do we need? Well, we're definitely going to need a function to increment and slide. So function to increment, slide and increment. Let's see, object along tree. Okay, so this means that we need a way of finding a particular node in the tree. Now we could do this with the depth first search, but I've got a feeling there must be a more efficient way to do this. I just haven't quite figured out what it is. So let me think. Instead of imagining this tree as a bunch of, a tree, like a binary tree that we search through, maybe there's a way to think of it as a list of, like an array of sorts, right? Where we keep a certain element in each array, and basically the idea is relatively simple. We go through, we go ahead and write this, and we do this, page, new page before. Instead of thinking of it as a tree, oops, sorry about that. Let's think of it as the following. We have, let's say 0, 1, 2, 3, 4, 5, and then we have internal and external. Hey, Gothic Death Eater. Okay, so let's do Nanyatan da Omai. What's the value of internal nodes that don't have letters on them? What's the value of internal nodes that don't have letters on them? We are not currently outputting that value of internal nodes yet, but it's going to be a sum of all of the external nodes that they've added up so far. So that's the idea. Let me go over here. So each of the internal nodes is going to be a sum of the external nodes. So here it's going to be like if these guys are 1, it's going to be, I don't know, 2 here. And then here it's going to be 4 because that could be 2, so on and so forth. So we just have to add them together there. We'll see if we need to visualize that in a bit. I haven't quite figured out the best way to do the visualization of this. So we kind of got to think about it a little bit more. Okay, so let's imagine the tree in this way. So first of all, we create a tree, right? This tree, we're just going to say it has one single 0 node. Okay, now let's do the vidder algorithm like we did before. And let's see how this works. Yeah, so instead of implementing it again as a tree, let's implement it as an array, and let's see what happens here. This is going to be really weird. So what are we going to be reading in? Let's do this. Let's read in A, B, C like we did before. Okay, so let's do, first we have 0 node. So we add A to the 0 node. So now we have A here. And let's, instead of writing down, okay, this is kind of complicated already, but let's do it this way. So now we have 1, which is root, and we have, one second. Let's see, we have 1, which is root, and then we have 0, which is A. Okay, now we have to create block 1, and now we move these guys into this guy here. So now we say 1, which is root, and 0, which is A. And this corresponds to the following tree. 1, A, 1. And let me think. This will be 0, and this will be 1. So in terms of the internal numbering schemes, A is at position 0, and root is at position 1. Okay, so now next we do the B. So we have right now 0, and we're going to add in, wait a minute. Shoot, I already screwed up. Let's try this again. Okay. There has to be an easier way to do this. Let me think. Anyway, okay, let's keep working on this because we're gonna need some sort of system to compare all of the nodes, right? So if we don't have an array, it's gonna be kind of difficult. And guys, I'm kind of thinking about this on the fly. So what's the order of the children of a node? The order of the children of the node is dependent on its position in the tree. So for example, let's go back a couple pages. With this tree right here, we'll say that we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Yeah, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. So we'll say this is node, I'll draw it in red, 9, 8, 7, 6, 5, 4, 3, 2, 1. So it's red from left to right and up. So the top node is the highest, the bottom left node is the lowest. And that's how the implicit numbering works. It's specific to this algorithm. So let's try it again, ABC. Okay, let's draw it out. So first of all, we have 0. We have only one thing in 0, and that's going to be 1, which is root. Let's call it 0, which is root. Okay, so that's easy enough. Next, we have 0, and what we're going to do is we're going to add 1. So we're going to say 1 is now root. Okay, and then we go through and we say 0. Oh, actually, wait a minute. 2 is now root. 0 is going to be our 0 element. So there's nothing in this. And then we say, we'll say not yet translated instead. And 1 is going to be, one second, A. Okay, so this corresponds to the following. Okay, where this is not yet translated. Okay. Then we move this guy and this guy into the next one. So now these guys move here to create a new tree that looks like this. Let's try 0. And of course the 0 node is still not yet translated. Then we say in 1 we have 2. Let's see if I can draw this differently. 2, which is root, and 1, which is A. Okay, so this corresponds again to 0, 1, 2. Okay, so now we read in a B. This is going to create 2 new nodes here. So let's go ahead and do that. So we're going to say at the 0 node, we now have 0 for not yet translated. We have B for at position 1. Let me think. At 1. And we also have 2, which is the internal node, which we'll call, I guess, just internal node. Okay. So we have an internal node there. Okay, so now at 1, we have 3, which is going to be A, and 4. All right, C Everett's, which is going to be root. And this corresponds to the following tree. This corresponds to a tree of, let me see, 1, 2, A1, 0, B0, 0, where these are, let me see, 0, 1, 2, 3, 4. Good. Everything seems to work out so far. Let's go and do page, new page before, and let's draw this out one more time. So 0, and in 0 we have the not yet translated node. We have B, which is at position 1. And of course we have the internal node. Okay, at 1 we have 3, which is going to be, see, what is it going to be? It's going to be our, what node is this going to be? 3 is going to be A. And then we have 4, which is going to be root. Okay, so now what we have to do is an increment and slide. So what does this mean? Well, this means we have to take our internal node here, and we have to move it in front of all of the A's in this block here. So this guy is going to have to move over here. And then we're going to have to increment everything. So let's see if we can do this with our simple array structure over here. So this means that we're now going to put our block number 2 here, and it's going to take position block number 3. 3 is then going to move to position 2. Yes. And then B should be still in position 1. Yeah, okay, so let's see what happens. So after doing this, we're going to have the following array. It's going to be, let's see. Oh, actually, all we need to do is change the numbers here. So this is going to be 3, and this is going to be 2. We increase the number of this guy, plus, plus, increase the number of this guy, plus, plus. So now we're going to have 0, and the only thing in 0 is going to be the not yet translated block. And in 1 we're going to have 2, which is, rather, let's do it this way. 1, which is B. 2, which is A. 3, which is the internal node. And 4, which is, hey, inventor stuff, which is the root node. Okay, so this corresponds to a tree of boss like ma. As I said before, no, the numbers represent the index in the tree. So this is going to be the following tree. We're going to say, let's see if we can draw this out. So we're going to say this corresponds here. So first we have 0, which is a not yet translated node. So I guess we'll just draw this. Maybe we should do it the other way. So let's start with root. Root's going to be 4. Okay, so this is root. Then what we say is we have, let me think, 3, which is the internal node. 3 is going to be this way. So here's our internal node of weight 1. And here is the next node, which is A. And that's going to be A here of weight 1. Then we have B, which is of weight 1. And we have the 0 not yet translated node over here. And again, the numbers represent here. So 3, 2, 1, 0. They're implicit numbering schemes. As I said before, the implicit numbering is important to the Vitter algorithm because it's what tells us what is in a particular block. Finally, root is now shifted to block 2 because it now has a 2 in it. So we go here. Let's just go ahead and rewrite this in the following way. So we're going to say 2, and we have 4, which is root. This is data compression, yeah. We'll see how far we get with this. This is actually a super complicated algorithm, and though it's incredibly cool, at the same time, it's kind of hard to implement, and I haven't quite figured it out. What I might do, guys, and I haven't fully committed to this yet, it depends on how long it takes me to do the my YouTube video tonight, but what I might do is I might take tomorrow off and spend the entire day kind of looking at this algorithm, figuring out how we want to implement it. So this next week when we do the implementing, it goes incredibly smoothly. But at this point, guys, we're kind of learning the algorithm and trying to figure out ways that we might look into it. So we're kind of, today's more of just almost a purely analytical day. Like, not analytical, but purely like pen and paper day, which is fine. You know, lots of that kind of stuff happens. But yeah, it is definitely data compression and stuff. Again, so I'm letting you guys know this now because I might take a day off tomorrow just to kind of, you know, because I'm going to be up really late probably working on my YouTube video and stuff because I've got a full day today teaching, ironically, data structures to people. We've got a skill pill at OIST, and I've got the first lecture on teaching simple data structures and things like that. Just simple things, lists, arrays, all that kind of stuff. So that'll be interesting. Yeah, I don't know why I signed up for that. I probably should have said no to that. But anyway, it's okay. I think it's going to be fun. All of the skill pills are super fun here at OIST. But gosh darn it. I don't know so much about programming. So I don't know why I signed up to teach that. I should have signed up to take it. But that's okay. We'll see how it goes. My lecture is, I think, pretty solid. Okay, so what do we need to do? Let's now add in the last letter, which is going to be a C. So this is where things get a little bit complicated. Page, new page of 4. Let's draw out the table. 0, 1, 2. And let's keep the tree over here. And then let's go from there. As far as I've gone on this during a course, will lossless and lossy image compression, with lossless and lossy image compression, even then it was only the basics. Yeah, this algorithm itself is, in a sense, still only the basics. It's just kind of complicated to implement. So in the 0 block, we have the not yet translated node, which is going to be at position 0, not yet translated. Okay. In the 1 block, we've got a couple of different things. We have on the far right, we have the internal node, which is going to be position 3, internal node. Then we have, let's see, next to that, we're going to have 2, which is going to be A. And then next to that, we're going to have 1, which is going to be B. And here we have 4, which is root. Again, corresponding to the following tree. 4, 3, 2, 1, 0. And then we go through and write down the things. This is going to be root. This is going to be our internal node. This is going to be A. This is going to be not yet translated. Forgive me for that one. B, and they're going to be connected like this. There. So hopefully this helps you see where we're getting everything from. Now what we want to do is add in a C. Okay. So first thing we do is we add in the C up here. So C is now going to be added in here at positions, let's see. So this is still going to be the 0 node. C is now going to be 1. And now we have a new node, which is of size 0. And this is going to be at position 2. Okay, this increases the number of everything else by 2. So now we have 3 for the internal node, or sorry, 5 here, 4 here, 3 here, 6 here. Let's make sure this works. So we're going to add in C of 0, a new node here. And let's see what we got. So we say this is still at position 0. This is now at position 1. and this one's at position 2. There's an internal node here. Okay. Now we say the not yet the. Let's see. B is going to be at position 3, which it is, but I am failing miserably at keeping my notation the same. B is going to be at 3 now. A is going to be at 4, which it is. The internal node here is going to be at 5, and root is going to be at 6. Okay, good. So everything is increased exactly in this way. So what do we do next? Well, now we do the increment and slide. So we say this 2, which is an increment internal node, which is currently at 0, needs to move over into the highest leaf, which is going to be this guy here. So now we're going to say that 2 is going to become a 4, and the 4 is going to become a 3, and the 3 is going to become a 2. So let's go ahead and put this in there. Just Google Huffman Forests. Mind confused? Why are there several nodes in the same index? There are not any nodes of the same index. Let me redraw the tree. There are absolutely no nodes with the same index. Not the way that I currently drew it. So again, we have the root node up here. We have these guys here. So this is our A node. This is an internal node. These guys do B1 here, C0, 0, 1, 3, 2. Not yet translated. 1, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6. There aren't, so far as I can see. Oh, these right here are, weights. And these guys are nodes with that weight. Okay, so the idea is that all of the nodes with weight 1 or with 0. So we have these are all the nodes with weight 0. These are all the nodes with weight 1. These are all the nodes with weight 2. So all the nodes with weight 1, all the nodes with weight, all the nodes with weight 0 here. All the nodes with weight 1 here. Weight 0. Weight 1. Weight 2. There you go. Okay. I'm gonna get another sip of water. I'm just super thirsty today. I'm sorry, guys. Also, for the record, guys, I am kind of making this up on the fly. So if you guys have better ideas, let me know. No, Bostic, not right now. We have this internal node right here. So this guy corresponds to that guy right there. So right now we have 2 0 nodes here and here, but we also have this 0 node there. So yeah, root will always be the highest weight. But right now, because we are transferring, let me see, hypergraph, inventor stuff, open link, see what we have here, a tutorial on generating a Huffman tree. Yeah, that's fine. We already have a Huffman tree generated. Not a big deal there. In fact, we've been doing Huffman trees for a while, and we have this very neat visualization of creating a Huffman tree. We're working on dynamic Huffman trees, which are incredibly, way more difficult. So we're kind of working towards that. Okay. So let's see what we need to do. Gosh, I've spent the entire day, like, no programming yet today. Okay. So now we add in, let's do Control-Z a couple times to get rid of that pink. Okay, so let's do Control-Z. Now we have to actually implement the increment and slide. Like I said before, this internal node here, which is now of weight 0, is going to want to be in position 4. Okay, so now we need to move this to position 4, which is going to be this position up here. Position 4. Yep. Okay, now this means that everything else is going to change position, right? So A is now going to be in position 3, which is this position here. And B is now going to be in position 2, which is this position here. Okay, so let's go ahead and do that. So this guy's going to be there. This guy's going to be there. So the new weight should be, let's draw the same table again. 0. Oh, actually, let's just change the numbers for now. So this is going to be 4. This is going to be 3. This is going to be 2. Now let me think. C. What happens to C? Well, C now is at position, let's see, 0, 1, 2, 3. It's actually in the same position. It's still a 1. So now we increment things. This guy has to be added 1. So plus, 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 plus. And we have a new table being generated. The new table is down here. Yep, it is right here. Okay. So now we do weights down here. Let's go down here. And let's do this. So 0, 1, 2. 0 is our not yet translated node. Now in 1 we have a couple of different guys. We have 5, which is an internal node. We have 4, which is an internal node. We have 3, which is going to be A. We have 2, which is going to be B. And then we have 1, which is going to be C. Okay. And then instead of a 2, we no longer have a 2 because this guy has increased. Oh, we do have a 2. Shoot. 2 is going to be, let me think. This guy right here. So this internal node is then going to shift over down here. So I think this is going to be position 5. So position 5, which is an internal node here. And then 3 is going to be root, which will be 6. Which corresponds to the following tree. Page, let's see. So 6 is root. Then we have 5 as an internal node. And it's of size 2. Then we have 4 as an internal node, which is of size 1. We have, let's see, next is going to be 3, 2, 1, C. So it looks like it's going to be A, 1, B, 1, C, 1, and then the not yet translated. Okay, so this is fine there. And again, even if we don't end up using this array thing to do the actual algorithm with, it's fine because this gives us a better understanding of what it is that we're actually doing. Okay, so now we've recreated those trees that we created at the very start. A, B, C. Now if we add in a D or something like that, it's going to be just about the same. The main thing is we have to find a way to keep track of all of these different blocks. And all of the nodes still have to point to, sorry about that. All the nodes still need to point to their parent and their sibling nodes. Well, sorry, their parent and their children node, so that we know where everything is. This is a little bit complicated, and I'm not really sure the best way to do this. But with 30 minutes left, let's go ahead and see if we can write down some general stuff over here. So we're going to have to, of course, void. One second, void, slide, and increment. Oh, and Gustorn, if you're looking for some example code, go to page 839. So 839 on that paper. Okay, it has some code on some stuff there. Another good paper to read. One second, let me go ahead and find it. If you're looking for more information, should be. One second. It's somewhere in here. Man, I'm so glad that I'm not working on my thesis proposal anymore. My paper stack is so much smaller than it used to be. Like seriously, this thing used to be the size of, used to be huge. Okay, there's one more paper to look up. And this paper, one second, let me get it out for you, is here. It should be written by, yes, it's still written by Vitter, so I got the right paper. Sorry, I just hit the microphone there, did not mean to. Let me go ahead and give you guys this paper too while I'm at it. Okay, the paper is entitled Algorithm 673 Dynamic Huffman Encoding. Let's go here. Algorithm 673 dynamic Huffman encoding coding, and it goes through the actual algorithm itself, written out in Pascal code. So here's the code here, and there you go. That is also somewhat useful. So it goes through all the different functions that we need, and it's a little bit hard to read, but that's kind of because it's Pascal code and I have trouble reading Pascal code. So just because I don't know Pascal code very well. On the upside, this paper is not so long. It's okay. I think it's what, 167. Let's see, it starts on 158. So it's about 10 pages long, which is fine. It should be, it's just really dense, so it's not that readable, but that's just my opinion. Maybe other people can do it pretty easily. Okay. So on the upside, we can now implement the Vitter algorithm analytically. Now we just have to think about the best way to hold all these blocks and everything else in the system. So slide and increment. I don't know what we're going to need for this. What other functions do we need? We're probably going to need some stuff like function. Oh, good. I wish I had. Man, lock-free algorithm. What actually is a lock-free algorithm? Lock-free algorithm. So one thing I want to point out, guys. Okay, interesting. Allows individual threads to starve, but generates system-wide throughput. Interesting. Okay. One thing to point out, because we only have 30 minutes left, I don't know how much programming I'm actually going to get done today. And as I said before, I think it is good to take one day off tomorrow, so that I can kind of recover from editing my YouTube video tonight, and I can spend some time working on this encoding theme. Now, one thing that I could do tomorrow, instead of working on this dynamic Huffman stuff, what I could do instead is I could work on a side project again. We could go back to working on the subroutine webcomic or something like that. I haven't quite figured out the best thing to do. So if you guys have opinions, I think I'm going to take a break from the Huffman stuff tomorrow. I think I've decided that throughout today. I'm definitely going to take a break from the Huffman stuff tomorrow so I can get a better grasp on exactly how we want to attack this problem. And of course, if you guys have suggestions, feel free to let me know. Now, what to do tomorrow? I can either not stream, or I could stream with a side project. And side projects include, I don't know, working on a small game that I have considered, going back to the subroutine webcomic and drawing some things with code just for fun. We've gotten much, much better at drawing things with code, so maybe we can get a lot farther. Let me think. Other things that we could do, not necessarily sciencey, lots of things that we could do. So if you're interested in me streaming tomorrow but doing a side project, let me know. But I am going to take a break from the dynamic Huffman tomorrow, just because I've been looking at this for so long. I'm kind of a little bit frazzled, and I've got a lot to do today. So I'm letting you guys know that. Again, let me know your opinions. Okay, so I've given you guys the two papers that we need to work with. Now, we have a couple of different functions that we're going to need to add in, and I'm going to be kind of following this paper that I just linked in terms of those structures that we're going to add in. So we need, let's see, a couple of different functions. And again, following this notation, we're going to need one function that is receive and decode, which basically takes in a new bit. Let's see, receive and decode repeatedly calls. So if I'm not terribly misunderstanding the algorithm, then you can store the internal external nodes in separate vectors where you pay attention to insert to the correct position and new nodes arise. Yeah, that's exactly what I was thinking, and that's kind of what we did over here. So the idea was that, I know it's super complicated, but we're keeping them all in different vectors in here. You get swaps and blocks for free. Yeah. So it's, yeah. Okay. Let's keep going. So we need a function to receive and decode. I misspelled receive. Okay, receive and decode. A function repeatedly calls a system function receive to read one or more bit of input until the input sequences of zeros and ones has specified path to a leaf. Actually, let's think about this in another way. Here's what we need. We need something to go through each individual letter and encode it into our tree. So let's do this. Let's say function to generate dynamic tree. This is going to be our general function here. So this function is going to be void And we're going to say, let's just call it Vitter for now. And we'll kind of change the name a little bit. Vitter. And what are we going to need? We're going to need the following things. We're going to need a string to work with. This is a string of letters, right? Now, what else do we need? I think for this algorithm, all we're going to need is the string to start, but we might need more stuff in a bit as we start thinking about it. Other functions that we're going to need. We're going to need a function, let me think, to create all the different blocks. So let's do create vectors of blocks. Okay, now this is where things are going to get a little bit complicated. I don't know the best way to do this. So like Gusterman said, we can store the internal and external nodes in separate vectors. That's perfectly fine. So if we do a vector of vectors, we can do this without too much trouble. So I guess what we want to do, if we have the length of the string, we could do this super easily, but it's dynamic Huffman coding. So we're assuming that we don't have the length of the string. Okay. So what we should probably do then, what do I need? If I don't need a vector, so I need a data structure that I can work with that allows me to, oh, I see what you're saying. You just want one vector for internal, one vector for external. Okay. Let me think. How about we create a separate struct for all of the blocks? So let me think. We have block internal, block external. So let's do this. Let's go up here, dd, 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 and let's do this. Struct block. And we do std vector. Okay, so we need a vector of, let me think. Std vector. And what we need to do is, we're going to need two of these guys. So it should be a vector of, I guess, integers, which is going to be, you don't need separate blocks. Internal, external. Okay, let me think. You define the leader of this block. Let's see. You get swaps if you define the leader of its block as the highest index node from nodes of the same weight, then you have your blocks right there. You don't need separate blocks. Wait, no, that's not true. If you define the leader of the block as the highest indexed node from nodes of the same weight, you have your blocks right there. I don't understand what you mean. So if we draw page, new page before, and let me just draw a super simple tree that's very easy to understand. So we do 4 as our root node, 2, 2, 1, 1, 1, 1. Okay, these are going to be numbered like so. So we're going to say 0, 1, 2, 3, 4, 5, 6. And we have the following blocks. We have this block, we have this block, and we have this block. Okay, so let me think. You don't need a separate... okay. So we define the leader of the block as the highest index node from nodes of the same weight. Where do we get the block from? So I'm not understanding. So this then is the leader of the block. So let's define this as the leader of the block. So we'll color it in, I don't know, blue. Leader of the block. Leader of the block. Leader of the block. Okay. Leaders. Okay. So, if you define the leader of the block as the highest index node from the nodes of the same weight, then you have your blocks right there. You don't need a vector of vectors if you define the leader of the block. Oh, are you just saying within the vector? So let's say we have, so let's see. This means we have a couple different blocks. So we have block, we have a couple different, So this is how our internal vector would look like. Yeah, I think I see what you're saying. Oh, no, I don't see what you're saying. We would have two vectors, in and out. And these guys would say the following. We would have internal as 4, 5, 6. And we have external as 0, 1, 2, 3. Highest index always a leader. I'm not quite sure I'm following, but let me see. Your internal would be 2, 2, 4. Yeah. We need the numbers though, obviously, because otherwise we can't point to the nodes. Would look like this. So, but how is that what you just wrote? This. How is this not a vector of vectors? Let me think. So we can do a number of things here. I'm sure. But you're saying we don't need a vector of vectors. So let me see. How do we... Yeah, you're right. I don't think we do need the vectors because we know which are of what weight. But let me think. How do we search through? How do we easily search through such that we know what all the weights are? Let me think. So obviously in the external nodes, we have 0, 1, 2, 3. Those are all of weight 1, so it's not that big of a deal. However, these guys are of weight 2. And these guys are of weight, that guy is of weight 4. So I guess let's color these their respective colors so I don't screw anything up. So these guys are in this block here, the purple block up here, and this is in the orange block. Okay, so that means the purple is of weight 2 and the orange is of weight 4. So what are we going to do? What we need to do is we need to find... every single day a customer is writing pseudocode for me, which is great, but I feel kind of bad. Okay, let's go ahead and keep trying to figure out the functions that we need. And again, if you haven't noticed, I might be a little bit scattered. This is because we're kind of starting the project. Obviously, once the project gets along, we're going to have way more stuff to do, and it's going to be way faster paced. But right now, because we're kind of trying to figure everything out, this is kind of the part where you guys can ask questions and we can try to figure everything out together. So again, if you have questions, totally let me know, and I will totally try to answer those questions as soon as possible. Everett, let's see, just left, Bossakma. Again, I hope that it's a little bit more clear now. I'm not sure exactly how much clearer I can make it. So let's see, I'm going to keep this block structure here until I see otherwise. We have the Vitter algorithm. Now, what else do we need? So we need something to basically manipulate this block structure. So let's do function to, we have slide and increment. That's definitely going to need the block in it. So let's say block. What are we going to call it? We'll call it block. Block set. I will change the name later. That's a horrible name. Okay, so now we need a couple other functions. We have string that's being read in by Vitter. That means that we're taking every single character and we are putting it into the block. Now, this is done pretty simply with a slide and increment command. So that's not an issue there. Now, these blocks, let's see. How do we go from a block to how do we go from a block to a node? Because that's what we need. We need a node. So let's take a look at the nodes that we have here. Write and quit. vi Huffman .h. Okay. Node. So we have character key, double weight, position Ori. And then we also have, let's see, left, right, and parent. Good. So we have everything we need for all the nodes. Let me think. So if we have all the nodes, let's say we have all the nodes in some sort of tree structure. In fact, because these are implicitly numbered, we might not need the tree structure. We might need the nodes. But let me think. We can probably recreate the tree with just the numbers in hand. Maybe. No, I think it's ambiguous. Yeah, it is ambiguous, so we can't do that. Darn. Okay, but what I might do is in this struct node, I might add in an additional character. Now, what we could do is we could always have these nodes sorted by number. So if we have a vector of nodes, maybe this isn't so bad. Let me think. Run quit. This is super inefficient, but let me just for now do an std vector of nodes. And this is what I guess we'll keep everything into this big block struct. So we'll say std vector of node. I'm sorry. And we'll call this 1 second, I'm thinking. We have internal and external, which are sorted by weight. And you want these guys sorted by weight too? Let me think. I'm trying to figure out how this algorithm would go in that case. So if we have all the vector of nodes, wait, let's just call these guys nodes. Okay, so if we have a whole bunch of nodes, before I think we did this as a priority queue, which is fine. Okay, so vector int internal key. Okay, what other functions do we need? Okay, so we have the function to slide and increment. We have the function that will actually do the main bulk of the code, which is again shown on, dropped a paper, which is again shown on page 839 of the original paper that I sent, this one right here. Okay, so what else do we need? Basically, I think that should be about it. Maybe this is a lot easier than I thought. It's not actually, but maybe it is. Slide and increment. Yeah. So then we just, basically we need update, which in this case we called vitter. Update will read in a leaf node. Yep. Okay, and then slide and increment. Anything else we need? Maybe not. Okay, so let's go ahead and remove this for now. And right now we might be able to just get away with these two functions. So let's put these down at the bottom underneath main. And I realize some people don't like me doing this, but that's how it is. Now the visualization is also going to be a pain in the butt. So even if we can get the dynamic Huffman code done, it's not going to be the easiest thing to go from the dynamic Huffman code to the visualization of the dynamic Huffman code. But I'm expecting best case scenario this to take a week. Worst case scenario, it takes a couple of weeks. That said, we spent a couple of weeks working on this Huffman algorithm over here on the left. So, you know, maybe there's more to it. Oh gosh, I'm not even doing this right. So let's say phrase. Okay, let's go down here, put in phrase. And I'm just gonna add in a quick ampersand here. Okay, another ampersand here. Okay, so I guess we've got 10 minutes left. We can still continue thinking about this, but again, as I mentioned before, there isn't really so much I can get done in what little time I have left to program in. So what am I thinking? I guess we can just go ahead and open up these guys and go from there. So let's do this. Let's do this. Okay. So vitter algorithm, what are we gonna do? Well, we have our phrase read in. So let's just kind of go through each element in the phrase. Okay. So reading the phrase, we know that we're going to have to go in and basically slide and increment every one of these leaves. So what do we need with slide and increment? Well, we're going to need to read in, what do we want to read in? We're not only going to have to read in the block set, but we're also going to have to read in the character itself. Now, do we want to read in characters, or do we want to read in a node of sorts? So what they have here is they already create the node, and then they read in the node. What we need to do, let me think. We could manipulate the block set all the time. We just need a way to very quickly point to all of the nodes in our block, or in our big structure here. So if we can find a way to very easily point to all the nodes in our tree, then we're set. The question is how to do that. So anyway, let's go through here. We know we're gonna have to have a loop in here. So for I in, oh gosh, what am I doing? I equals 0. I less than phrase.size. Then we do plus plus I. And we go through the following. I misspelled phrase. And I forgot an int. So let's do size t. Here we are. I do not have ADHD. Why? Do I sound like I have ADHD? Phrase. Here we are. We go through all of these guys. Now what do we do next? Man, now I feel really bad because I guess I've been really, really bad at describing what it is that we've been doing up to this point. I thought I was doing a pretty dang good job. That's okay. Okay. So let's go here. And what do we need to do? We need to output. Bah. I don't like this. Should we create the node and read the node into slide and increment? Or should we just read in each individual letter? I think we should read in the letter. So let's read in, let's go here. Open link, let's see. Okay, so node find leader, constant vector node, internal, node block member. Okay, so let's see, what do we have here? Internal sort by weight. Do you give these kind of lessons every day? Yeah, I'm here every day from 5 to 7 o'clock a.m. Okay, some auto block start iteration, but they aren't really lessons. It's more like I'm trying to learn an algorithm, and you guys are along for the ride. Auto block start iteration, find if, let me think. STD begin, internal, and internal. So you want the internal nodes to be weighted, let me think. Vector of nodes, internal. Oh yeah, I needed a star with the internals. Yeah, okay. So now we do vector ST begin, internal, ST end, internal, node, find if. I've never actually used find if before. Block position is equal to ST distance. Never used distance before. While block position is less than internal dot size. If internal block position weight not equal to block member dot weight, return internal block position -1. Errors should never happen. Okay, let me see. Auto block start iteration. So let's see if we can figure out what this find if thing does. So find if. It's probably, let's see, find if C++. Find if. What do we have here? Find if returns an iterator for the first element in range. Okay, sounds fine. Distance. C++. Find if finds the first element where lambda is true. Yep. And distance is going to be calculates the number of elements between first and last. Yeah, could have figured that one. Okay, so what are we doing? We're saying the first iteration is going to be begin, internal, and internal. So those are the ranges. And then we're saying wait, good. Then we say, so this is calculating the index of the block. Okay, yeah. I see exactly what's happening here. So now what are we returning? We're returning the internal block position -1. If internal block position weight, let me see, not equal to block member dot weight. Yeah, I do theoretical physics. Born to reborn. That is exactly what I do. I am in the Quantum Systems Unit at the Okinawa Institute of Science and Technology. No, not like Sheldon Cooper. I'm actually real, and I do actually real things. So let's see. What do we do? Actually, a lot of my friends absolutely hate Big Bang Theory. They think it's like the worst show ever because all it does is just make fun of nerds. Like that's the entire premise of the show. Oh, there's revisions. No, there aren't. Okay, so actually what I'm going to do is I'm going to copy this and put it into the code that we have so far. Let's go here. What do we want to do? Let's put it here. And let's see if we can figure this guy out. So let's do function to find the leader of a block. Okay, so what do we have? Vector node internal. That's reading in these guys up here. And of course, these need to have stars in them, so I was incorrect earlier. Okay, so we have all the internal nodes. As long as we keep them in different node vectors, this should be fine. So auto block start, SD end internal return. You'll need include algorithm. Okay, fair enough. So let's do this, include algorithm. Okay, I guess that's where find if and distance are. Okay, so begin internal, return wait. I think so, yeah. I've used algorithm before. Okay, so what's next? Find leader, block position. Okay. So we should then be able to create a vector of nodes. Do we have a vector of nodes already? We should be able to create a vector of nodes. And then find, let's see. So what you're saying is instead of having these guys of internal, external, we have this as a node star. Okay, let's think. So we can find then the leader of the block. And how would we find, I guess, do we need anything else? But yes, okay. Not only do we need the leader of the block, but we also need all of the internal block members. And this is because I don't think anyone's too dumb for scientific languages. I think people just think they're too dumb. I think, in my opinion, I don't like when people say they're too stupid to do something. It's just personally like, I always think I'm too stupid to do something, and yet everyone seems to think I do a lot of stuff. I mean, not here on stream, but like in real life. I promise, in real life I do things. Okay. So guys, it's 6:57 in the morning. I'm going to probably call it. Now, the reason I'm calling it is because I normally end my streams at 7, and I need to really think about how we need to get this done. Gustrin just gave me some code to look at, and I'm not really sure exactly the best way to do this. So on the one hand, we need to find a way to find the entire block so that after changing the leader position, we can go through and we can slide all of the elements along the tree, right? So we need some sort of what is it? We need to find some way to do the implicit numbering scheme. Born to be born. I actually do quantum stuff for work. Let's see. I do superfluids and Bose-Einstein condensation and stuff. Most people say they like quantum stuff, but when they actually do the quantum stuff, they don't actually like the quantum stuff because it's all math. It's literally all math. Okay, so this is super messy right now, and I admit that, and I apologize for that. But we've got a lot left to do, so let's go ahead and think about how we want to do this. If you do block end position, let me think. Would that actually give us our index? Oh. Yeah, it would. You're right. I didn't even think about that. You're totally right. It would. Let's add that in. Plus block position. And let's do this. I'm going to add in some notes here. I don't know anything about that. Actually, you probably know more about it than I do. So let's do main. Just adding in a quick note that is main. Okay, so this is a lot of stuff to kind of read and sink in and understand. I'll be honest, this is not the easiest thing we've ever done on the channel. We've definitely done easier things, like graviton and stuff. I don't know. I know absolutely nothing about particle physics. Particle physics is so far removed from what I do that it's not even something I've ever had to look into. In general, that area of quantum, though it uses quantum, I don't usually consider that quantum. I usually consider more like cold atom stuff quantum, and that stuff more particle physics. That said, there's definitely a lot of overlap there. Okay, guys, it's 7 in the morning. We've done a lot of stuff, talked about a lot of stuff. We haven't actually implemented a lot of stuff. What I'm going to do is I'm going to take a step out off of the Vitter algorithm tomorrow, and we're going to work on something else, a side project, or we might take the day off. I haven't quite decided yet. We'll kind of figure out how things go. You can also do vector, but I think it'll end up being harder to manage. Yeah, I'm not sure. So here's what I'm going to do. I'm going to write down a couple of different ideas, and we're going to see how far we need to do. So vector, vectors versus weight managed nodes. Okay. Do you think humans have a soul? This has nothing to do with quantum mechanics or anything like that. My personal opinion is that I would like to believe people have souls. Whether it's true or not, I don't know. Can't be validated. So I don't really know. Anyway, guys, I'm going to go ahead and end the stream here. First time I met a clever guy. I'm not that clever. Like, Gusterin is way more clever than I am. Thanks, man. I appreciate that. But I do quantum physics, and then I just say do. Anyway, guys, that's it for today. We spent a very long time going through pen and paper how to do this algorithm. I'm very happy we did. That was what I wanted to get done today. And we're kind of sort of thinking about how we want to move forward with this algorithm. We've got a bunch of ideas. I think Gusterin's ideas is spot on what we need to do. We just have to think about how we need to do this. So we have to, if we're going to do it this way, we need to figure out the best way to organize our big block of internal and external nodes and go from there. Okay, a lot left to do. Gonna take a day off from this tomorrow, and we will get back to it after that. If I do stream, it will be a side project tomorrow. I've got a couple of those that I kind of want to do that don't have any relation to physics or math or really programming in general. They're just side projects, you know, like drawing with code or something like that. So we might try that tomorrow if I have some time. Otherwise, I might just be up super late working on my my YouTube video, so it might be late, or I might just not come. Again, I apologize for rambling and saying the same thing over and over again, but that's it for today, guys. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, where we do something. I haven't decided yet. Again, I apologize for being so vague about that, but definitely on Monday, my time, we will be back working on this, the Vitter algorithm. Again, that is Japanese Standard Time, 5 to 7 o'clock a.m. every day, except for maybe tomorrow. Might take a break tomorrow. Haven't decided. Anyway, guys, thanks so much for watching. I'll see you next time. Bye, guys.